I'm now inside the dome of the George Abel Observatory after a short trip, good for your health, and I can show you, standing next to the telescope in the dome, what it means to have an astronomical telescope and why we need it in the shape it is. So this is a 16-inch diameter telescope, and there is a mirror at the end, as you may see from the reflection. It is so big because it needs to collect a lot of light. The sources in the sky, the stars, galaxies, nebulae, are very faint, and in order to improve on what the naked eye does, we need to have a much wider opening, much more light gathering power compared to what the pupil, the tiny pupil of the eye, does. That's one of the main reasons why telescopes, including this, but the really professionally large telescopes, need to be huge and ever bigger. The second reason you may need a telescope, if you look at the skies, is because you want to magnify what's there compared to what you see with the eye. And in much more specific terms, you want to have a better resolution of the images. And this is achieved by having the light travel a long way between the optical surface, the lens which produces the image, and the plane, the location where the image appears. And I can show you by moving this around a bit. This is the tube, and it can move about this axis, so you can see it is of a certain length. This is not the distance between the lens and the image plane. It is only a short part of it, because there's the mirror, the optical light comes in, is reflected back, there's another mirror, is reflected back again, is distorted on the way, and the effective distance between the front and the end is 4 meters, so a lot longer than the distance between the lens in the eye and the back of the eye, which is determining your resolution power if you observe with naked eye. The telescope, as you may have seen when I moved this, is moving about this axis, which is bizarrely tilted, right? You can see there it is tilted, and in fact it is parallel to the rotation axis of Earth. Why would this be? Because the Earth, as we all know, rotates in a day around its axis, and with it the telescope. So if we observe a star and have a very long exposure, this star and the telescope and the Earth would simply rotate away from the line of sight to the star, and the image would leave a trail rather than a dot, as you would want. And therefore we need to compensate for this by rotating the telescope around an axis which is parallel to the Earth's axis the other way around. That's what this mount achieves. We would quite like to show you how this works. We can't just now with this telescope, because it's not dark yet. It's almost raining, as it quite often is in the UK. We have cloudy skies quite often, so not too many clear skies where we could demonstrate this. Luckily, the Open University owns 2 robotic telescopes, not much different to this in size, at a prime location in Tenerife, on top of Mount Teide. And you can see this now on the image on your transmission. The 2 domes roughly in the middle belong to us. They are called Parrot and Coast. And these telescopes allow us to make use of an enormous number of clear skies in the year, about 300 or so. We have a little time lapse for you that demonstrates what it looks like over the course of a day. The shadows get longer, it becomes dark, the domes open, and you see a very busy activity of these telescopes. They close and open as things go along. The same at night. This is the Milky Way moving across the sky because of the Earth's rotation during the night, which is exactly the effect I was talking to you about, the rotation. If we did this in a still, so this is a very long exposure of the night sky, not an animation, but just the shot of the camera is open for a very long time, you see these concentric rings of stars that circle the northern celestial pole. And this is taken from Tenerife, from the mountain there. And I have a question for you here, which you may be able to answer in the chat. How long do you think this image was exposed for? Was it, let's say, a few seconds? Was it a few minutes? Was it an hour, 10 hours, 100 hours? what you think. Let us know what you think, and we tell you what the answer is later in this labcast. So have a good hard look at this and let us know what your opinion is. These telescopes, the beauty about these telescopes is you can operate them from home when you continue to study the pathway of physics or astronomy and planetary science and are on the correct modules, because you get access to these facilities and can take images with them of your own. And in the next slides we have a number of images that were taken with Pirate, and you could do so yourself if you come to that stage in your curriculum. This is a globular cluster, 100,000 of stars on a very small space, condensed. In the next one we have a galaxy, a very far away island of stars, similar to our Milky Way, where you can see in red hydrogen emission nebulae showing spots where star formation is happening. And in the next one, this is close up in our own Milky Way, an emission line nebula, as we call it, which is excited due to the irradiation, the heat and the power and the energy coming out of nearby newly forming stars. So this is a star formation region, and there is the end state of a star which shed its outer envelope. It's called a planetary nebulae. These are just nice shots of the night sky, but obviously even in Tenerife sometimes the weather isn't quite as good as it should be. And what do we do then? Is there other ways to access the star, the cosmos around us, and observe it or measure it? And of course there are other wavelengths to try out, and one you can try out when you study physics or astronomy and planetary science with us is the radio regime. So the wavelength range of radio waves is probed by another remote access telescope we own, this time here, based here in Walton Hall, a 3.5 meter radio dish called Arrow, actually just outside of the building I'm in now. This radio telescope measures the 21 centimeter domain or wavelength range, which is important because hydrogen, the most abundant element in the cosmos, has a quantum transition which emits radiation of this wavelength. And so because hydrogen is everywhere, we get this emission from everywhere we look on the sky, everywhere in our Milky Way. And therefore, by measuring this wavelength range, we can probe the location of hydrogen gas in the interstellar medium in between stars with our radio dish.